Hello, everyone. Today we are discussing Chapter 8, Understanding Populations. In this section, we're going to be looking at how populations change in size. So get ready. We're going to go over what a population is. We've talked about this before, but let's just review. A population is a group of organisms. They are the same species and they live in a specific geographical area and they can breed with each other. A population is a reproductive group. So these organisms will breed with each other and they will produce more members of their population. The word population refers to the group in general, but also the size of the population or the number of individuals it contains. So the population is all of those individuals of the same species that can breed with each other. Of the world has about 7 billion people in it. We're up to about 7.5 billion now, actually. So lots of people. Some properties of the population. One is the density. This is the number of individuals of the same species that live in a given unit area. Dispersion is the pattern of distribution of organisms in a population. And this population dispersion may be even. It could be clumped, it could be random. So this is looking at how the organisms of a population are distributed. So size, density, dispersion, and other properties can be used to describe these populations and predict what will happen within the population. So how does a population grow? Well, populations gain individuals with each new offspring that they have. And they lose them with every organism that dies. The resulting population change over time is represented by this equation. So you have change in population equals births minus deaths. So if you have 100 organisms born and 20 die, 100 minus 20 is 80. So the change in population size would be 80. Growth rate is how we express this increase in size of the organism over a given period of time. So growth rate equals the change in population, which is the birth rate minus the death rate, divided by time. So what the change in population is divided by the time it took for that change. So over time, the growth rates of population change because you have organisms being born, organisms dying, and so this can increase or decrease the population, the growth rate. So you can have a positive growth rate, you can have a negative growth rate, or you can have a zero growth rate. If the deaths are more than the births, you're going to have a negative growth rate. If the births are higher than the deaths, you'll have a positive growth rate, and if they are equal, you'll have a zero growth rate. So how does a population grow? Well, for the population rate to be zero, the average number of births has to equal the average number of deaths. It would remain the same size if each pair of adults produce exactly 2 offspring, and each of those offspring survive to reproduce. If the adults in the population are not replaced by any new births, the growth rate will be negative and the population will shrink. So how fast can a population grow? Well, normally the populations stay pretty steady from year to year because you have organisms dying and then organisms being born at a pretty steady rate. So, but these are the factors that control the size of the population. So in the long run, the factors also determine how the population evolves. Now, if you have something come along like a fire and it destroys a lot of the population or a disease, then those things can change the population growth a little more quickly. The reproductive potential is the species' biotic potential. Remember, biotic means living. Is the fastest rate at which its population can grow. It's biotic potential. Okay, this rate is limited by its reproductive potential. So if each animal, each female that has a baby only has one baby, that's the limit of its reproductive potential. Most organisms in the animal kingdom have multiple babies at every birth. Its reproductive potential is the maximum number of offspring that a given organism can produce. So this is the maximum that it can have. So like some species of fish can lay hundreds of eggs at a time. And there are lots of animals like that, so that it gives those eggs a better chance to reproduce, or to survive and to reproduce and have their own babies. Some species have a much higher reproductive potential than others, like bacteria can reproduce very, very quickly. Mice reproduce very quickly. Insects. Okay, so there are things that can increase their reproductive potential much more quickly than others. When this reproductive potential increases, the individuals have more offspring at a time, or they reproduce more often, or they can reproduce earlier in life. So, like for example, human girls can't start having babies until they've gone through puberty. And so that is around 10 to 14 for most girls. After that point, then girls could start having babies. Up until that point, they cannot. So that can limit the reproductive potential. When an animal can have babies starting earlier in life, they have the ability to produce more offspring. Reproducing early also shortens the generation time, or the average time it takes a member of the population to reach the age when it reproduces. So for example, humans, we have generations, and our generations are pretty far apart normally, normally at least 20 years. And that's because most of the time, women do not have babies before the age of 20. It does happen, but a lot of times women wait until after they're 20 to start reproducing. So that is the generation time between their parents, them, and then their children. So it's a lot longer for humans than it is for animals in the animal kingdom. Small organisms like bacteria and insects have short generation times. They can produce when they are only a few hours or a few days old. So their populations grow very quickly. Large organisms like elephants and humans, they have to wait a long time before they become sexually mature. And then, so they have a lower reproductive potential than insects. Exponential growth is logarithmic growth, or growth in which numbers increase by a certain factor in each successive time period. So for example, if you look at the graph, you see time is across the x-axis, population size is the y-axis, and you can see that over time, something happened that caused that population to grow exponentially. It grew very quickly. Exponential growth occurs in nature only when populations have plenty of food and space and have no competition or predators. So if there's an explosion of population explosion of bacteria or mold when it grows on a new source of food. So you might look at a piece of bread that starts to mold and it might have a little dot, and the next day the whole thing might be green. And that's because it can reproduce very quickly. In exponential growth, a large number of individuals are added to the population in each time period. So for example, if you look at the graph, you see that this is the number of months. So it's going up by just months. And you can see between the 12 and the 16 month, the population grew from about 150,000 to 800,000. That's a huge increase. That's what we call exponential growth. Now, populations can grow, but most of the time they don't have that exponential growth because there are limits to population growth. Natural conditions that keep the populations at a pretty even amount. So a lot of times the natural conditions are not ideal and they're not constant. And so populations cannot continue to grow forever. Eventually they use up the resources. The resources that we have on Earth only support a limited amount of living things. So it's up to those individuals to find those things in order to survive. So this is where natural selection comes in. If you have in a given environment, only some members of the population are going to survive and reproduce because they're going to have those characteristics that are going to allow them to reproduce. They're going to have access to the food and they're going to be able to have more offspring. Carrying capacity is the largest population that an environment can support at any given time. Things that limit the carrying capacity are the amount of food available for that population. So the population can increase past this number, but it's not going to stay at that increased size because the environment cannot support a large amount of individuals. Like right now, it's deer hunting season. Why do we kill deer? Because if we have too many of them, they're all going to starve to death. So you have to keep the population in check. Can't really predict carrying capacity because it's hard to predict what's going to happen in the environment. A drought could come and kill a lot of the plants, and that's going to put a huge limit on the amount of animals that can live in that population. So that can affect carrying capacity. So here you can see the dotted line is the carrying capacity. That's where the population is supported by the environment. It can overshoot carrying capacity, but then as it starts to run out of resources, you can see the population is going to decline, and then it might recover, and eventually it's going to stabilize, and it's going to hang out around that carrying capacity. Resource limits. A species reaches its carrying capacity when it consumes a particular natural resource at the same rate in which the ecosystem produces that resource. What does that mean? It's only going to be able to consume what's available for it to consume. The natural resource is then called a limiting resource. So the supply of the most severely limited resources determines the carrying capacity for the environment and for that species. There's also competition within a population. The members of the population use the same resources in the same way, so they have to compete to get to those resources. So instead of competing for a limited resource, members of the species compete indirectly for social dominance or for territory. Social dominance is very big in the animal kingdom. Okay, a territory is the area that's defended by another animal. The territory of value is not only for food and shelter and space, but also for the breeding potential that it contains. So the potential for them to reproduce. Many organisms have a large amount of energy, and energy competing with members they need more energy, so they're going to need more fuel. There are two types of population regulation. Population size can be limited in ways that may or may not depend on the density of the population. So you have density dependent or density independent. Okay, we talked about this a little bit. Density dependent depends on the population. Deaths occur more quickly in a crowded population. This type of regulation happens when individuals of a population are densely packed together. Limited resources, predation, and disease result in higher rates of death in dense populations than in sparse populations. Density independent is when a certain proportion of the population may die regardless of the population's density. It does not depend on the amount of animals in that population. This type of regulation affects all populations in a general or uniform way. Severe weather and natural disasters are often density independent causes of death. Okay, so density dependent, it depends on the density of the population. Density independent, it does not depend on the density of the population, how many are there. Okay, so now you will answer some questions based on this information. You can go back and review it at any time, and please let me know if you have any questions.